Well, what is geometry? One could say that topology is geometry, and Professor Campo, okay, but I'm going to talk, that everything, starting from topology, that everything is geometry. Geometry is more wide than we think it is. But I'll be a little bit more restricted to the point that two things that look very similar. One is geometry, what geometry occurs in the other one, when it depends on the eyes of the okay, on personal opinions. All right, now what is geometry? So it is interesting that Cartan refers to the original Riemannian geometry, the geometry until 1917, as those spaces as pseudo-spaces, not as pseudo-Riemannian spaces, but as Riemannian pseudo-spaces, because there was not a concept of geometric equality. Okay, equality of figures. In some very wide sense, you would say yes, but instead of telling it what it is, okay, what we had in mind, I read from his work selection. This is from a conference he gave, a talk he gave in 1936 or 35 in Oslo, honoring Sophus Lie, who was Norwegian. Oslo, the capital of Norway. Okay. And he talks about the development of differential geometry at the beginning of the end of the 19th century, beginning of the 20th century. During the 19th century, there had been, apart from projective geometry, there was somebody in 1944 who, so to speak, saw that Euclidean geometry, at that time, geometry was not really very well recognized. So the idea, what was emphasized by this guy in 1844, I don't remember what it was that Euclidean geometry was a particular case of a projective geometry. Anyway, but other than that, the topics on which Cartan was interested, he had in mind Riemannian geometry, and on the one hand, and the Erlangen program on the other hand. The Erlangen program of which the author is Felix Klein. Okay, the idea was clear. And he says that at the beginning, Riemannian geometry was almost as mathematics unrelated to the rest of physics, the rest of mathematics. I read, he said, so he's going to present 3 points of view, okay, about the evolution of geometry. He says the first point of view is the one of the Erlangen program of Felix Klein. It has its origin, okay, several truths on origin, I can say that. For Felix Klein, each group of transformations, I'm reading from French, so pardon me, defines a geometry whose object is the study of figures invariant under the transformations of a group. In gross terms, the point of view of Klein consists in retaining and keeping from Euclidean geometry as fundamental notion the notion of equality of figures, together with the axioms attached to the concept of equality of figures, of which the most important is the one according to which two figures equal to a third one are equal to each other. Of course, there is a technical name for that.
This is not equal, congruent. You can displace one with superposed.
I'm reading. Okay, sorry. I don't want to say more than I said. Okay. Then a little bit later, he says, The Erlangen program has been, for several years, viewed as constituting the synthesis, the final synthesis of all the geometric figures, his opinion. Now he's going to consider, so far he has only talked about Klein. Now everyone is going to enter the picture. He's going to go into the second and the third points of view. And he has in mind the paper by Riemann about the hypotheses which are at the foundation of geometry. And he explains, before saying what the two additional points of view are, that Riemannian geometry is a simple generalization of Euclidean geometry. But whereas Klein keeps from it, above all, the notion of geometric equality, Riemann retains only the notion of distance. Those 2 points of view, pushed to their last consequences, are totally divergent. The notion of distance disappears in the geometries of Klein, or the most general geometries of Klein, and the notion of equality of figures disappears of the most general Riemannian geometry. The notion of group is no longer in this at the base of the Riemannian geometries. However, this notion of equality of figures can be introduced, but in two very different ways, which are going to give rise to the 2 additional points of view. Okay, he says, in the first period, which goes until 1917, 1917 is the year of the Lechita connection, independently discovered by Lechita, Scott, and Hesselberg, as if the time had come for it. Until then, one can talk about geometric equality, not even as a parallel transport, which have the property, since it is the comparison of vectors at 2 different tangent vectors at 2 different points of the manifold depends on path. We don't have the transitive property. If we move a vector from here to there along one path and we move it along another path, we end up with different results in general. Although there are connections which respect that. Okay. In that epoch, with this point of view, okay, in the first period of the 1917, Riemannian geometry has been seen as the theory of the invariance of a quadratic differential form, quadratic symmetric, with the G mu, the theory of G mu, in n variables xi with respect to the infinite group, and when meaning infinite group, it doesn't mean infinite element, infinite Lie group. Okay? In the sense that, okay, we have a rotation, there are infinite rotations even in 1 dimension. No, but that depends on only 1 parameter. Okay, infinite Lie group, so depending on infinite independent variables is set encore kinetic. Yeah, still set encore. From this point of view, that Klein, the author of the other theory of geometry, views Riemannian geometry in the conference that he gave in Vienna in 1894, okay, before Lechita. Now, through an analytic transformation taking us from certain variables xi to x primes, the quadratic differential form becomes another form, the quadratic differential form, and the formulas tell how one goes from the xi's to the xi's and the gi's to the x prime i's and the g prime i's. These formulas define an infinite Lie group. Not just an infinite group, an infinite Lie group. I'll go to the next. This point of view admits immediate generalizations by considering any other infinite group isomorphic to the general group in n variables. I can skip on this. Okay, this is interesting. It is clear that when it encompasses Anglo in French and in geometry, all the problems of equivalence with respect to any group, finite or infinite. The question then is to know to which point of view it is legitimate to attribute, okay, a geometric character, as we are dealing with problems so general and to which often, souvent, one has to resort to pure analysis. That is, okay, there are certain generalizations which appear to lose contact, but what we modern people consider geometry and resort to pure analysis with assumed topology. He's wrong.
The text, I'm not sure that is the right interpretation of this text.
Oh, okay, so you understand French?
Yes.
So I'll read in French.
No. I understand the text, but then the text, what it says, is more simple. So, for instance, the notion of Lie group is the group of all diffeomorphisms from one manifold to the other. You can say that this is as it is, but it's not a Lie group.
Okay.
There's no Lie algebra.
Okay. So, I'll just say what he says. There is no response, remember. Is this geometry or it goes far beyond geometry and we should consider the analysis? In some cases.
So this analysis and geometry is the same.
Okay, he is making a distinction, obviously. If one is a lawyer or a philosopher, then by reading the sentence, he's making a distinction. Okay? There is, evidently, there is no 11 okay. Okay. He continues, Mr. Velen, several years ago, declared geometric all that which competent people look as such. I subscribe gladly to this opinion, although competent people are not always in agreement, even in mathematics. In fact, the systemization made by Klein has been adopted without resistance as a legitimate extension of the domain of geometry because it provided a unifying principle of different theories previously, I repeat that, developed and of which nobody would say that they were not geometry. Okay? Et auquel personne ne refusait de reconnaître les caractères géométriques. Okay? Yes, for the theories, okay, to which one can apply this idea of what is a geometry, based on the group, those geometries were accepted by everybody to be geometry. In the, and I finish with this part, in the case that we are interested in, is the same thing. Now he's going to contrast a why yes and why no. Okay? We would be tempted to say no. No, what was the question? Let me go to the beginning. The question is posed of knowing at which point it is legitimate to attribute geometric character. So, all those, so the response is no. No. Because the point of view from which we are looking at Riemannian geometry, that was infinite E group, okay? Coordinate transformations, does not make evident, and in fact, it hides what is geometry in geometry. What is geometric in geometry? What he's saying is those infinite transformations, that group of infinite E group, masks what is geometric, then what is geometric. This is what made him, his answer to this problem, is what made him develop his theory of affine connections after first formulating the Klein program. Okay. But, in contrast of that was why not. Now he's going to say, yes, why it is legitimate, to attribute a geometric character to those such a large group of transformations, infinitely group. The general scheme that we have considered brings in a series of problems of nature manifestly geometric. And then he mentions the textile geometry of Blaschke and the School of Hamburg. All right, now I'm going to jump because now his opinion, his conclusion, and what I'm going to present, is actually what Cartan did in differential geometry, and what I have pushed further to reach the boundary of quantum mechanics. It is certainly the notion of geometric object would not be present in Verne. Il est certain que la notion d'objet géométrique, it wouldn't occur to him, to Verne, at the point when, apart from the geometries of Klein, only Riemannian geometry existed in the first stage of development of geometry. It was perfectly logical that Verne and his school and so on would have that point of view so general. But that point of view is not sustained, maintained, but by later constructions to which it provides a unifying and creative principle. But that only has a verbal existence. It exists in words. It provides a framework, a cadre, that those geometries do not fit. Okay? Like saying, well, they are artificial constructions and later on he says they are not related to what has been traditionally called geometry. I leave it at that because now it is important also that is Cartan also. Now Cartan and Grassmann, this is pretty important. Grassmann is famous for Grassmann logic, which is based on the stereo product. But Grassmann did something far more important than Kant. In my opinion, if you look at it, all you were there. From a historical point of view, he created something called the progressive regressive system, which looks a lot like Clifford algebra. Then Clifford would take, it was a mess. Grassmann created many concepts that are modern up to this day, okay, which were only found in the 20th century, second half, also the first half. But after recognizing by Dieudonné, for instance, the tremendous importance of the concepts that Grassmann created, he said what Grassmann created was a terrible mess, because he had to make many concepts not well organized. So he, after telling all the good things of Grassmann, he says, okay, this was a terrible mess. On the other hand, there is a paper in 1908 by Elie Cartan where, about complex numbers, it only has only 150 pages. He devotes 17 of those pages. He talks about everything that had been done. He devotes 17 pages to Grassmann. 2 pages together, different reactions. All right, instead of saying this system of Grassmann is a mess, he says the very fruitful system of Grassmann. But why Dieudonné had such a poor opinion and Cartan has such a great opinion? Because apparently Cartan knew how to do it well. And if you look at the papers that Cartan wrote, immediately after 1908, 2 of them within a period of 2 years had already the title of the moving frame or something like that. What was the great problem with Grassmann? He had something that we could call classes, which would be kind of equivalent a previous stage of grading. So the different classes approximate something like different grades. But we put in the same class, as with the same grade, points and vectors. And that had consequences. Okay, and it was a terrible mess, but Cartan knew how to solve that.
Now, the notion of equivalence relation is becoming unique.
Pardon?
The notion of equivalence relation and the short way of talking on this came after Grassmann and before Cartan. So the language to talk about this was improved.
Okay.
So really, Cartan could be more clear than Grassmann.
Oh, okay, I mean, I don't have...
But the content did not change so much.
Well, no, in one respect, point and vector, for you, that doesn't have importance. For us, and especially for the physicists, will have importance because, thanks to the point of view of Cartan, we are going to cover, okay, what physicists do not know how to do, and if you know this differential geometry, you cannot avoid it. So please give me a chance, if you wish, we will have a session after 5 o'clock. And you're supposed to go to view, okay, you have to respect. All right, so the circumstantial evidence is there. Grassmann, I don't want to remove any merit from Grassmann. I just want to say that in the description that Cartan does, okay, of Grassmann, you see, and he knew what he was talking about, points and vectors when he was in class. Whereas when we do Clifford algebra, we don't mention points at all. Okay, now, finally the learning program. The idea...
Points, I think, are the scalars.
No.
They are 0 dimensional.
Well, maybe it's not okay. Yeah, but remember, okay, the fact that the scalars, one would think that because the 0 dimension they will be assigned. The scalars, it has R1. The points are going to be Rn. Okay, so, yeah, let me now go to Brian, otherwise I will Klein, first, as you say, was already here. But in any case, even to this day, people believe a group.
Klein was here, trust me. Klein had a good language.
Okay, anyway, they developed separately. And, Klein, you said Klein was not clear, fine. And Grassman was clear, at least it was for Captain, apparently not clear to the me. Okay? So, it was clear because he had such nice words. The fruitful system of Grassman. Captain says very clearly. Okay, so, what is wrong with the Klein program, or what was incomplete, or whatever? First, it is not a matter of just a group. It has to be a group and a subgroup with a certain property. I will not enter the property. It is a little bit technical. More, one has to first distinguish between them. Okay? Not totally equal. Klein geometries, what we call nowadays, Klein geometries and generalized Klein geometries. For instance, at the affine plane is a Klein geometry, but if we have a surface, even without a metric, or if we have the Euclidean plane and a surface with a metric and so on, one of them is elementary, also called Klein, then it is going to be associated with a system of integrable differential equations, whereas that system is not integrable, then we have a generalized geometry of that type, generalized Euclidean geometry or generalized affine geometry. So, first, group and subgroup. And second, subdivision and distinguishing between the elementary geometry, Klein geometry, or Klein geometries, and the generalized. For instance, the sphere in this Cartan contest is a generalized geometry. However, okay, it was not considered like that by Klein. It was simply a matter of having an infinitely group rather than a finitely group. All right. Now, in order that we don't get into confusion, I'll speak of vector space on the other hand and Euclidean vector space. A Euclidean vector space is a vector space where we have the dot product. Okay? That's a vector space without dot product. And affine space is one which is more than a vector space. And we call Euclidean space, not Euclidean vector space. Okay, but Euclidean space would be an affine space which is more than only Euclidean vector. Now, the difference is essential for everything that comes from now on. Okay? Assume I have an affine space here, the plane, and two-dimensional vector space. We don't need a metric for the time being. In the vector space, we have a special element, the zero. And all the bases are equivalent. In the affine space, there is no special point, and all the points are equivalent. So,
what can you do less in a affine space than in a vector space?
Wait, let's go slowly. Please, okay? Wait, because there is going to be something. Here, all the points are equivalent.
What are points? You don't talk about points.
In a affine space, the points of the affine space, okay?
They're all equivalent.
Only one?
They're all equivalent only.
Yes! Okay, but the point is that, right, here we only have equivalence of the frames. Okay? I'll repeat. So, we have to see the argument, okay, under this hypothesis. In the vector space, again, there is a special point, the zero, and all the bases are equivalent. Here, there is no special point, and all the points are equivalent. Now, the idea is to use, vector spaces in a affine space. Then in a affine space, it looks like linear origin. For instance, people like him, I know, he defines an affine space precisely by saying it has the properties that if I take any point, and I use it and are associated with the zero of a vector space, then any other point can be described by a vector and there is a property. Okay, now we have assimilated vector spaces, okay, to our affine space. But notice the points were all equivalent. Now we've chosen one, so we have breaking the equivalence. How do we restore the equivalence? We restore the equivalence by doing the same, okay, at all points. By adopting that, okay, of choosing this point and making it the zero, we think we have brought all the vector bases with this here assigned to this point. Okay? But now we have to do, in order, if we want to return to the equivalence of all the points of the affine space, if we want to return to that, then we have to do exactly the same at each point. So we have an enormous, a pair of a point in the vector space that we call a frame. Now we have an enormous amount of frames, but they have a very nice structure. Namely that at each point of the affine space, we have all possible bases, and we call that set of bases, we call it the fiber of the affine, the fiber of the bundle of frames, of the frame bundle. This is the fiber, here there is a blue active, which is the same everywhere. For instance, in affine space, okay, here we have in the basis space, we have the calculations. And here, over each fiber, we will have all the linear transformations for that particular thing. Questions?
How do you work directly with affine spaces?
What do you mean? How do you define?
How can you work directly with affine spaces?
How can you what?
Work directly.
With affine? Well, we work directly. The idea is what is behind it. Okay?
You can say that in a affine space you have the notion of barycenter.
In affine space
you have the notion of barycenter. In a vector space you have the notion of addition. You do not need to make the affine space first a vector space and then
I don't like that because the consequence, I want to develop a point of view which they have not seen, because the consequence is that physics will follow. So the proof is in the pudding. Okay. Now, so affine space. Now we have affine space in the frame bundle. But we could have Euclidean space and the Euclidean bundle. The difference would be that the fiber, instead of being constituted by all vector spaces, it would be constituted only by the orthonormal basis. So a pair of
how do you know of the normal?
Pardon me?
Of the normal in
Yeah.
So that's why the base affine space was an affine space. You have no
We associate with, if we can associate with the affine space, okay, if we restrict this bundle just to this set of bases,
a set of bases. Why are those bases of the normal?
No, not yet. Over there, affine space, they are not orthonormal. If we restrict only ourselves only to the orthonormal basis, then that is a Euclidean space. Okay. Now, suppose we have
So that restriction is equal to defining a metric equilibrium.
yes.
That's a category.
But I didn't want to talk about the metric yet. Okay, because what is the metric? For some, it will be just a lot of problem.
That's a categorical composition. What you're describing here is categorical composition.
Okay. Now, if I have an eggshell, I can take a little piece, but I can move it around in the sense that, okay, you take it from If this is the area, you take a small piece from here, it doesn't fit everywhere else. So, okay, all the points are not equivalent in an eggshell. It is like if we assign a metric to it, it is like, yeah, it is a generalized Euclidean space. We can have generalized Euclidean space or generalized Euclidean space. It is Euclidean only, okay, we would say infinitesimal, I don't like the term, okay, only, but infinitesimal, okay? And therefore, what we have to do is to, in order to make it enter into the same framework, we have to treat the structure, okay? Those two groups, the group and the subgroup, we have to view it from a differential point of view. Then it can be assigned to each small piece. Okay? That would be like the Earth, consisting of an infinite, of a very, very large number of football fields. Okay? It is only approximate. Okay? Because if we take the eggshell or sphere, we break it into pieces, never mind how small the pieces are, okay? All of them, never mind how small they are, they have the curvature, okay? And the radius of curvature written there. Okay? So, equation for the structure of so, in a finite space, satisfies P, that the point, Q is the point that we chose specifically, to which we assign the 0, plus AI. I could write these with matrices so that I don't have to use indices. And say, but here it is better, I could write the EI, here the metric for the transformation, okay, and here the AI, the basis we started with. That is for a finite space. Now the restriction is that our bases are going to be orthonormal. Differentially, dB equals dQ, which is going to be. But Q was going to be a fixed point. Therefore, it is 0, and this is going to be therefore AI, and DEI equal AI.
What means differentiating the point?
What does it mean?
You said you differentiate the point. I do not understand. What means differentiating the point?
No.
I do not.
We have a function. Okay, differentiating the point. If it's actually differentiating, I thought that it didn't need an explanation. Or the fixed point. The fixed point forever. And now I'm going to take another frame. Another frame is going to be I don't care what this experiment. And now I'm going to refer anything else to this.
So never got it a difference. Never got it the difference there between the two models.
There is a frame bundle over here, so we are in the frame bundle. Okay, so now we can write this as BAI, and then you can about
What is the key? Second row, what is the key? This.
DA?
No, the first part. DE is this the.
DI, okay. In the case when I start with the flat space, the EI exists. Okay? As soon as you generalize it, I can avoid DI, although it is usual entire experiment why there is some justification to write it that way, even though it is not an exact closed differential, much less exact. Okay, for the time being, you know that in Euclidean space, okay, say you take a curve, the tangent vector, you can always refer it to the AIs. Okay, so this, if I invert this transformation, okay, I am going to have dA and the matrix X A minus 1 dI. And I'm going to call this, so I'm referring to the dI itself, and I'm going to call it omega I j ej, okay, or di and j, and here I'm going to do the same, dA to the minus 1 ei, okay, and I'm going to call that the omega I dI. It is very important. So, now, since this is differential, since these are differential, although differentials are not time pieces, when we evaluate the loads as functions of curves, and we have time pieces of curves, then I'm going to differentiate. I forgot to differentiate this one, which gives omega ij plus omega ji equals 0. So, we forget about this, and if I consider this as a differential if, instead of obtaining omega I and omega ij as I give them an initial, something I get from my pocket, and put it in there. This system in general is not going to be integral. Okay? So, is not going to be integral.
Sorry, what case is not going to be integral? Can you repeat?
This system is considered as a differential system. Okay, the system to be integrated to obtain C and dI. Okay? In the case we have, where we have computed those in terms of those, obviously it's integral because there is no differentiation. Okay? But the generalization is going to consist at this point. At the point where, okay, I take again omega I, a differential one form from my pocket, as well as this one. It is important to realize that this is a system only in the E's, whereas this is a system which is not only in the E, okay, that depends on the dI. So here in reality, we have two systems. This is a system by itself, this one. And all that is another system. But this first one is not a system by itself. Because first we need to have an dI. And in general, those are going to be Gaussian vectors. Okay? And what has to connect to them? Alright, so what is the generalization of that? I take the dB, I formulated the following system. dB, which is going to be omega I. And the integrability conditions for these are going to be dB. The differentiation equal to 0. Because here we have fixed basis, so we will differentiate twice. I wait for you to check the face. Okay? If we differentiate twice, we are going to have dt equals 0. So dDp in this case is 0. But when I use, okay, in general this is not going. If I give the omega I and omega ij from my pocket, then this is not going to be 0. It will be 0 in a particular case in which the omega is over space, but not in general. So you give me an omega I and an omega ij. I said that the omega ij, not just the omega I, because if this is going to be in a piece of our manifold, if this is going to be like in a finite space and having that like a Euclidean space, we need to have as many independent one-forms as the number of values in the group that define the affine from the Euclidean geometry. So, in general, and we physicists are not used to it because this is not the way they teach us. These are going to be independent of those. I can formulate them, okay? I get them from my pocket. So, in general,
what is the second row of the equation?
who's talking openly?
The second row of dDp.
These were the continuations.
So is it the wedge product?
Yes. Here this is a wedge product. Here it is not needed or no, because this is a differential form and this is a zero form. Okay, vector value. So, in general, if I compute this quantity in a general case, it is not going to be 0. And whatever the di is omega and let me change notation di and di minus omega j omega ji. So in the final case, okay, I'll continue with the system di equals omega half. I have to differentiate. So it will be omega ij. Then usually change of the parameter because I know what is going to happen. Okay, d omega il minus omega ij omega ji ei. Something wrong here with this. Let me go right here. di equals d omega ij minus omega ij dj, which is going to be j omega k dk. Alright? So, common factor, if I use the same value as I take here, so I'm going to change the j to k, because it is a contraction, you can do that. So, therefore, we have the di equals d omega ij. Now, this is going to be 0 with the those that I was getting originally, but not with the ones I got from my pocket. So, normally, when we are doing differential geometry, we are allowed to write, okay? For instance, df equals something plus g dy. I am in the plane. I have a function in the plane. probability no f exists unless the integrability condition is satisfied. Namely that the partial of this with respect to y equals to minus the partial of g with respect to x. So that the sum will be 0, so that the d is 0. And yet, if we do not make a fuss, at least in certain branches of mathematics, to write df before we know whether that equation is integrable or not. We simply say, aha, I know that equation, and if f exists or doesn't exist, or the system is integrable or no, it's not integrable. Okay. However, in physics, probably in mathematics, people get very mad with writing this. We write in this. Because of the d equals 0, which is very important, okay? But very important, but when applied to scalar value differential form, okay, people will not like to write this notation, okay? But that comes to you if instead of writing it that way, which gives the impression that we have differentiated something, when in reality I got it from my pocket. And my pocket is definitely full from day to day. Okay? If I take, so I asked the secretary how in Romania I have lost the information to create only this symbol, and she did. So we remember.
Another question, Professor. Maybe it's a bit provocative. What is the advantage of this compared to geometric calculus, where you have all this out of your...
Okay, you were here. Okay? And that's the problem, but probably I'll answer that question.
Okay.
Alright? Then the text here is trying to do what I'm going to do. Okay? Rich geometry. Nobody has done. The great Kirsten and say, oh, the progress done in theoretical physics, and he mentioned some work by the guy at the Yorkshire, I think it's a in the astronomy was his name. Lassen, yeah, Lassen. I said, this is an anecdote about the anecdote, okay? Because you say, aha, before we didn't know whether the geometric calculus was any way of theoretical physics. Now we know the answer. Casting has come out of there since 64 when Heston published his famously wonderful book. Nothing! That is nothing, that's peanuts! And you will judge by comparison. Okay? So, one could have a symbol like that in order to make explicitly the point that we don't have P here, but something that we have introduced by hand. Where sigma I is all that. And the another symbol like that. Of course, the final extension of this would be to put here d omega following d g and g. But I don't want to do it unless necessary. Now, what is the integrability? We are given that. What is the integrability conditions for this system? The so-called Transylvania. Namely, You will see that clearly because there are other terms, but the other terms which do not have this or that vanish because that equation vanishes identically when the torsion is the curvature plus 0. This is the torsion, this is the curvature. So, you will say, how does he get from here to there? Okay, first you get all the terms. Okay? And then you look at them and you see, aha, these vanish identically with this, and only those terms survive. Similarly here. I ignore this one. Because, oh, pardon me, this is my, okay, yeah, because you can't complete. I think I'm going to be my unknown plus. Anyway, you do all the differentials and you apply it and you end up with that. Okay. So, this system constitutes the analysis. The integrability conditions for this system of equations. If it is integral, then we recover, okay, the Euclidean group and its, okay, from all that, first from all this, we will recover not because the omega is there. We will cover the subgroup, the group in the fibers, okay, the linear group with this condition, we will recover the O3 or ON, whatever it is, and with all that, we will recover the Euclidean group. But otherwise, so, for two reasons then, the idea of the group and the subgroup are only relevant infinitesimally, so to speak. Okay? But still there is a connection. So what is important? For that reason, and for this other reason, which Cardan said, la métrique ne contient pas, the metric does not contain all the geometric reality of the space. The geometric reality, I mean, the essence of the space is contained in the equations of the structure. And the equation of the structure is the differential system. This one, or the one we saw the other day, where there is not an affine connection or a Euclidean connection, and there is only a metric defining it. The one we work with, do you remember? Okay? We take the other day with this equal 0, which happens to appear here also, and then we can have that and we have this, where we have only a metric structure. Alright, so the equations of the structure. So from now on, from this perspective, we will categorize the different geometries of this type by the equations of the structure. Not by the group. Of course, the groups of the equations of the structure are related because of the groups, and we put it there 0 and 0. Okay. Projective transformations, why I'll go very quickly over there. Okay. Now what time we should be through already, right? What time is lunch? 1 or 1:30? 1:30. Okay, so I think whatever in the evening, instead of in the afternoon, instead of talking about salad, I talk completely this, and then I have computation and we go home. Okay. Questions? Are you busy by now? Too much? At least you have an idea. You will catch from time to time some subjects, or not? Yeah, I'm talking to students. Okay. Now, projective transformations. I want from this perspective, is more unlike a fine geometry, projective geometry, than physical geometry is. And I emphasize this point because physical geometry is going to allow us to geometrize classical physics. Okay? I put first answer just 2 points in order to go briefly into this. In a fine transformation, can represent this. Some vector P equals Q plus AI and EI. So, as a matrix, I could write P, EI, okay, column matrix. Zeros, or column zeros, the matrix A. Okay? So, this now starts to have the flavor of homography, where we represent a transformation in n dimensions by a matrix in dimension n plus 1. Okay? What is the problem with this? Normally, if we have a translation with certain parameters and the linear transformation, then we say, for instance, say it is a rotation. Okay? The inverse transformation has as parameters of the translation the same ABC, the same AI with a minus sign. The opposite of this translation is 1 with the opposite sign. But the inverse transform, the inverse matrix of this one doesn't have here. The inverse of that is it's 1, 0, e to the minus 1, but here instead of having the AIs, has something like a minus 1 AI, or minus, I think, something like that. So, the parameters of the translation, of the English translation, are here. So that is an inconvenience of the trying to represent it, okay? If we want to represent the affine transformations in the form of the projective transformations, which normally are defined as homographies, we have that problem. That problem, that, for me, unwanted feature, which has ideally, okay, but there is more. There is more. I would like to have, if we look at Euclidean geometry, in Euclidean geometry, we have what I call the displacements, which are the translations and the rotations. And if we do a fine geometry, then we want to, okay, consider that as a generalization of Euclidean geometry, and in addition to the translations. And the rotations will have those linear transformations, which are those rotations. And they contain, for instance, the elongations, and also instead of having perpendicular frames, we close up or extend and open up the axis. Okay, so we can follow from the Euclidean displacement, we can go to the affine displacements by identifying first the displacements of the more strict geometry. Here, we lose track of that because by doing the inverse transformation, we don't have the parameters minus AI. Okay, in addition, an unwanted feature of the homographies from some point of view is that the same projective transformation is represented by an infinity of matrices which differ by a multiplication factor, and we know why. So it would be nice to have just one representative. And Cartan chose to add the restriction not to have just one representative and still have the good property to demand for a final transformations that then to demand that the matrix that the determinant so we will have that property is concerned and the product. Okay, still we have the same, we still have the homographies, but we have removed the condition that we can choose a proportionality constant and instead demand that the determinant be one. That's a possibility. But for a line geometry, that doesn't work that way. Okay? I don't want to extend myself too much. But if I want to look at projective, at what we could call the projective displacements in the same way as I spoke of the Euclidean displacements and later on of the affine displacement, the question is, do you have a question, Alex? No. Sure. Don't be afraid. No tengas miedo. ¿Qué te molesta? ¿Nada? Oh. Yeah. The question then is, what could I add to the translations and the linear transformation, which are the affine transformations, in order to have the full projective proof? And what we could add are the homologies. What are the homologies? The homologies are, say, you have an origin, here a line, and you have some, this is going to be B, okay, and you have some constant factor K, and you take any line from here, and each point, you assign another point such that the cross ratio of these 4 points, one pair and the other pair, so we say this one, okay, is a constant. The constant would be K of a cross ratio. Look under in the internet or wherever under homologies. Well, homology is a name that appears in many places, but homology for the transformation. Now, notice that we have to complete the matrix, we only need n transformations. So n additional parameters, and this produces 2, B and K. But things come out very nicely if instead of getting introduced, you consider only the homologies, or they divide by a certain number, say 1. Now 2 parameters use the 1. And now, by considering, for instance, other axes, to make it simple, you could have n different homologies, and they are going to complete this feature. So the homologies with such that KB is a constant constitute the additional transformations that you will consider as additional projective displacements. There might be other solutions because the realm of projective transformations is humongous, but this covers the matrix. Now we forget about the 1 because the property of if I multiply 2 like these ones, okay? So I multiply 2 by lambda and then I multiply the 1. Because if you multiply 2 like this, you don't get 1 in there. Okay, that was to give you an idea. Now I'm going to go to the equations of structure. The equations of structure are not interesting in. I was getting them from Cartan at different levels. But you will see a difference between the two. I have not studied their relationship. I'm not interested. But you will see And in the same year in which he wrote the second paper on the theory of affine connections, he wrote a paper on projective geometries. So by then, it was very clear for them what the projective, the study of projective, generalized projective spaces. Okay? And then in 1937, I think, he wrote a paper about the moving frame and so on. Okay, and he came with a different system. Now, by writing affine transformation as a homography, okay, as a matrix, yes, as a matrix, the equations of the structure are still going to reflect the type of structure that we have in affine geometry. Namely, there is going to be the capital omega mu and the capital omega mu. When he wrote in 1937, they look totally different. So let me write to them and go now. Yeah, I can write this. Now, 1924, equations of the structure of projective geometry, generalized projective geometry. There is going to be capital omega equals whatever, then omega 0, 0. And omega 0, right? And omega I. Let's not enter the details. What is interesting is how it compares with what he wrote in 1937. In 1937, he wrote, Because if I proceed in another way, you're going to say, oh no, the basis space when I have Lorentzian connections is simply like the basis space for Riemannian geometry, except that when you use the metric, the signature of the metric is going to be different. It's going to be the Lorentzian signature. Therefore, I'm going to go the indirect way. So what are the equations of the structure of physical geometry? Of course, there are several schools. None of them, there is the Romanian school of differential geometry, the Russian school, the Japanese school, there is Hanover from South Africa, which came before them. It's ended the American school, which was promoted, developed by the 16th Church. Okay, so I'm going to write the equations of the structure of Transylvania. This is not what we have. This is not what we have. This is Transylvania. This is like what we had before. What is going to change? That on the right hand side, okay, now we are going to have the following. Here I have said space-time to speak in with Dracula. And we have the translations in the space-time. Then we take basis. Okay, so here we have the coordinates x mu, which are time coordinates for us. Physicists are very important. Okay, the x mu, which are time, and the xi, the Cartesian or boundary space coordinates. And here we are going to have the Lorentz homogeneous. Okay, Lorentz. Here we have 4 parameters, which are the demonstrations, and here we have 6 parameters. The frame under them is going to depend on 10 parameters. Now, one can reorganize this set of bases in the following way, such that in here we have for what we call several names, a space of elements, not only in use, or the direction, the boundary of directions, okay, the boundaries, that anyway, coordinates, the coordinates would be x mu, is going to be a third-dimensional space, where 3 of the parameters from here, which would be the velocities, are here, and there we only have, say, the polynomials. Okay? So, the equations of the structure are going to take the same form. On the left and on the right, we are going to have R, mu, nu, lambda, omega, nu, omega, lambda, plus. So, the invariant forms are going to be here. The omega nu's are going to be here. And also the omega ZYs. And the omega J's are going to be here. Plus S, mu, nu, I, omega nu, omega ZY. And here, what we are going to have in our space R, mu, nu, lambda, rho, omega, lambda, omega, rho, plus S, mu, nu, lambda, I, omega, lambda, omega, 0, I, plus T, mu, nu, plus T, mu, nu, I, J, omega 0 j. The omega 0 i's are here, they are called horizontal forward, and the other one, the omega j, I want to put in vertical. Okay. Those are, if I remove those terms, then it looks as if I have studied the version of Santa. In reality, there will be one more change. Namely that this doesn't mean the same thing in the Fisher boundary as it means in the Riemann boundary. Okay, I could take a Riemann boundary and refibrate it instead of this branch and refibrate it here, but then the meaning of in that refibration, the meaning of those two changes. And the Fisher boundary is extremely interesting because 0 becomes E0. Okay, just a simple, just an overlook of Fisher geometry. Okay, look at the changes. They are irrational. They are much less than here. In the geometry is closer to projective geometry, generalized Fisher geometry. Okay, I will not talk because there is little time about what is the elementary Fisher geometry. Okay, the elementary Fisher geometry is the geometry of special relativity, viewed in different ways. Okay, we don't lose the Lorentz transformation. We can have the Lorentz transformations, but we can also have greater generality. So, I forgot, okay. Two things. Shall we continue the afternoon, or do I follow a little bit more, or what? Because the most interesting part of physics is how we use structure. If I add teleparallels, namely that the Euclidean, the Lorentzian curvature, okay, that one which I cannot obtain from the metric, but independent from and from when I put from my pocket, when I pull the omega ij's, those determined by themselves the Euclidean curvature without resort to the torsion. So, remember I said, just this line constitutes a system by itself. Not the first line, the second line. So, the beautiful, I talked about this before, in case there is not. In the afternoon, I have to talk about Keller geometry, but by then you are probably Keller properties very lost. Whereas from the feedback I've got today, you are more interested in already in the afternoon when I started to talk about particles and so on, more interested than what we did in the previous days. Okay, so I'm going to go to this. Let's compute, okay, the autoparallels or lines of constant injection, or for those of you who have seen general relativity, okay, the dq along the curve equals 0, that gives you the equation of motion, okay, but with a Levy-Chita connection. If we do this with this structure, what do we get there? Unify the equation of motion of its general relativity together with the Lorentz force. Of course, the Q and the root M do not appear there. They only come from anywhere of quantum mechanics. The mass of an electron is what it is, not because of classical physics. It will have to be looked upon in quantum physics, not in classical physics. And this is only for classical physics. So, one has the equations of motion that we want. Now, what about the first layer of equations? Here in Fisher geometry, we can separate the capital omega 0 from the capital omega ij. We can separate them. Okay? So, we look at this element and take only the, when one develops that, they are going to be turns like this, and also quadratic turns in the others. If we only take that, because the field is relatively weak, and ignore that, what happens is that this sigma 0 is some constant, when we call it lambda, F, where F is the electromagnetic field. Where did I get it from? Here. Okay, by developing this, by developing the mathematics. So the first pair of Maxwell's equations is in the first Bianchi identity. Where is the Einstein's equation? This is pure geometry. So we have a set of Einstein's equations. How? We take that the affine curvature is 0, but we write the connection as the sum of the Levi-Chita connection plus something called the contortion, which one takes from the torsion. And one gets a series of terms. There is basically, and there are basically three groups. Then there is the group which only depends on the metric and derivatives. There is another group, okay, which depends on the contortion, thus on the electromagnetic field. And there is another group which mixes the two. And you can, this contains this more geometrization of Einstein's equations. The geometrized Einstein's equations are in the Ricci or in the Einstein contraction. So there you have, and here the gravitational energy, okay, is not just defined because the Levi-Chita connection doesn't allow anything else. It's not only defined I would say globally in the sense of the physicist, okay? It's not locally, defined at a point, okay? You can only say, aha, the energy momentum contained here is so and so. Here, no, it is well defined. And then there is an additional term, which is the interaction of electromagnetics and gravitation. And where is the gravitational energy? Well, it is in the Ricci tensor, or in Jewish, okay, in the mother of the Ricci tensor. Because we are used, aha! And the equation of gravity is the Ricci tensor equals so and so. And we could want to keep that scheme. Forget it! The Ricci tensor is going to be, okay, one more term in the equation that says that the sum of all currents, including the gravitational current, equals 0. Where is this more difficult? The second pair of Einstein's equations. Well, remember what we found, that if we know the structure of the space and the exterior derivative of something, we could obtain the interior derivative. The second pair of Maxwell's equations is about the interior derivative of the electromagnetic field. If we can get it canonically from the equation of structure, we are going to have the second pair of Maxwell's equations. Except that on the right-hand side, instead of having current, electromagnetic current, we are going to get the electromagnetic current, but in terms that we do not see charge times velocity. But what we are going to charge is a certain combinations of the torsion of the electromagnetic field. And there is going to be room because the electromagnetic field is here for other components. But for that, and go beyond, go to electricity. But for that, we need more to continue with this. And it is too late. So in the afternoon, when I have to talk about the speeches originally, I will continue with this picture, and because I want to take you to the very, very bottom of quantum mechanics, because it is possible to geometrize, if you know the right mathematics, to geometrize classical physics and unify gravitation and electromagnetism. So new things. I cannot realize that I have to look at this. Okay, I still have the gravitational energy. I was struggling with this because I still was thinking of the format. Ricci equals, okay, and now forget Ricci is one more current. Okay? and something else. Very most important. Somebody else at the same time as I did 1990 plus minus 1 year, also obtained the same connection as I did to connect with electrodynamics. But what we did was not legal. But our intuition allowed us to say, it is not legal, eventually it become legal, like, I don't know, sex. There is no lady here. Okay, things that were not legal were not well seen at one time, now they are well seen. Okay, become legal. The evolution of civilization is due to those who break the law a little bit at the time. Okay, why did I say that? Yeah, Transylvania connection, okay. Remember that in time, look, all other people also is running. Another guy, the guy from whom I learned physical geometry. We were looking for a connection which would have a certain property. You go to physical geometry and you find that in all of them, when you compute the autoparallels, all of them contain, and that finish with in 3 or more sentences, all of them contain the Lorentz force. You're going to say, how is that possible? Assume I have a standard connection. Okay? And now, only a few of them, only a particular case, gives you the Lorentz force. Now, you are saying, we refibrated on the finger bundle, and now all of them, like what I'm saying, give you the Lorentz force. How is that possible? Well, that refibration appears to have the property, okay? In the refibration, the meaning of what the superscript 0 is changes. So it is as if the components of the capital omegas reorganize. So, with the connection that we discover and we describe in terms which are not appropriate because we didn't know physical geometry, I only have a tiny bit of an idea. So what I have learned on physical geometry, I phoned the guy from which I have learned, something like in school, the second time I went, and I told, hey, look, the physical capital, the solution to the problem of obtaining the equations of motion for the electromagnetic interaction is in so and so. But this is obviously has a problem. And he said, oh yeah, this is capital omega 0 in physical geometry. He realized immediately, I had realized that had to be physical geometry, but I would not have known how to write it. He said, look, eventually I sent him a paper. He didn't even open the envelope. He already said, he already translated it into physical geometry. What he told me, he knew a lot of mathematics. Jose, I tried this and this and this and that, and I didn't find a geometrization which would make sense. I would not have obtained the result in 1,000 years. Takes time work. Thinking, okay, pedestrianly, not rigorously, okay, in physics, we were able to find the solutions, which then a good topologist for the differential topologies will make it clear. And I think that's good enough. Thank you very much.
So, one question. We are beginning the certificate of attendance. This afternoon, you must take. So, Jose must sign. So, let us go to lunch.